Welcome students to this lecture of the unit Chemical Bonding and Molecular Structure. In this lecture, we will discuss the following topics: ionic bond and its characteristics, approaches towards ionic bonding, energy considerations in ionic bonding, Lattice and solvation energies of ionic solids, Born and equation and Born-Haber cycle, polarizing power and polarizability, and lastly Fajan's rules. Ionic bond. The ionic bond is the electrostatic force of attraction between two oppositively charged ions. That's a positively charged cation and a negatively charged anion. It is formed due to the complete transfer of electrons from one atom to another atom. An ionic bond is formed between an electropositive metal atom and an electronegative non-metal atom with an approximate electronegativity difference of 1.7 on the Pauling scale. The formation of ionic bond between two atoms can be visualized as: atom A transfers an electron to atom B. In the process, atom A gains the positive charge and atom B gains the negative charge. The two oppositively charged ions are now held together by electrostatic force of attraction to give the ionic compound AB. Electrovalency. The number of valence electrons either lost or gained by an atom during the ionic bond formation is called electrovalency. Let us discuss the formation of ionic bond with reference to various ionic compounds. First of all, let us take the example of lithium fluoride, LiF. In the formation of lithium fluoride, the lithium atom loses one electron to get nearest inert gas helium's configuration, that's 1s2. Whereas the fluorine atom gains one electron to get the nearest inert gas neon's electronic configuration, that's 1s2, 2s2, 2p6. Thus formed lithium positive ion and fluoride ion, they get attracted towards each other to form the ionic compound lithium fluoride. The electrovalency of lithium is 1 since it loses one electron. The electrovalency of fluorine is also 1 since it gains one electron. The electronegativity difference between lithium having the electronegativity 1 and fluorine with an electronegativity of 4 is 3, which is greater than 1.7. Hence, the bond formed is an ionic bond. The second example that can be taken is that of sodium monoxide, Na2O. In the formation of sodium monoxide, each sodium atom loses one electron and oxygen gains 2 electrons. While doing so, both atoms will get the nearest inert gas neon's electronic configuration, that is helium 2s2 2p6. 2s sodium gives 2 sodium positive ions plus 2 electrons, while as oxygen gains the 2 electrons to give oxygen 2 negative anion. Thus formed 2 sodium positive ions and 1 O2 negative ion. They combine to form sodium oxide as given in the equation twice Na positive plus O2 negative. They give Na2O, which is an ionic compound called sodium monoxide. The electrovalency of sodium is 1 and that of oxygen is 2. The bond between sodium with an electronegativity of 0.9 and oxygen with an electronegativity of 3.5 is ionic since the electronegativity difference between them is 2.6. Another example of an ionic compound is aluminum fluoride, AlF3. The aluminum atom loses 3 electrons and each fluorine atom gains 1 electron to get the nearest inert gas neon's electronic configuration, that's helium 2s2 2p6. Thus formed aluminum 3 plus and 3 fluoride ions combine together to give aluminum fluoride, that is AlF3. The electrovalency of aluminum is 3 and that of fluorine is 1. The bond between aluminum with an electronegativity of 1.5 and fluorine with an electronegativity of 4 is ionic, since the electronegativity difference between them is 2.5, which is higher than 1.7. Now the factors that favor the formation of ionic bond. In general, the bond between two atoms gets ionic nature when the electronegativity difference between them is large. Numerically, it should be greater or equal to 1.7 on the Pauling scale. Since the ionic bond is electrostatic force of attraction between cation and anion, the factors favoring their formation also favor the formation of ionic bond. Now the factors that favor the formation of cations. The first is large atomic size. The ease of formation of cations increases from lithium to cesium in first A group with increase in size. Second, low ionization energy. The removal of electrons is easy from atoms with low ionization energy values. Hence, these atoms form cations easily. For example, first A and second A group elements readily form cations due to low ionization energies. The third factor responsible for favoring the formation of cations is low charge on cation. For example, among sodium positive, magnesium 2 positive and aluminum 3 positive, the order of ease of formation of cations is sodium positive greater than that of magnesium 2 positive greater than that of aluminum 3 positive. That's sodium positive is formed more readily than magnesium 2 positive and magnesium 2 positive is formed more readily than aluminum 3 positive. Fourth factor is the octet electronic configuration. The cations with 8 electrons in the outer shell, that is octet configuration, are highly stable and hence are formed readily. Whereas cations with 18 electrons in outer shell, that is pseudo-inert gas configuration, are comparatively less stable and hence are not formed easily. The electronic configuration of calcium 2 positive is neon 3s2 3p6. There are 8 electrons in the outer shell, that is octet configuration, hence it is formed easily. Whereas the electronic configuration of Zn2 plus is neon 3s2 3p6 3d10, that is pseudo inert gas configuration. Hence Zn2 plus is formed less easily than calcium 2 positive. Now the factors favoring the formation of anions. The first factor is small atomic size. Atoms with small atomic size attract electrons strongly and hence can form anions readily. The second factor is high electron affinity and electronegativity. The atoms with high electron affinity and electronegativity gain electrons easily and hence form anions readily. For example, the halogens, 7th A group elements can form anions readily due to small size, high electron affinity and high electronegativity. The third factor is low charge on anion. The formation of highly charged anions is difficult since the addition of successive electrons to the atoms becomes difficult due to repulsion from electrons within the atom. Hence, anions with low charge is formed readily. Among carbon 4 negative, nitrogen 3 negative, oxygen 2 negative and fluoride ions, the ions with low charge, that is fluoride negative, is formed readily, whereas the formation of anion with higher charge, for example that of carbon 4 negative, is difficult. The order of ease of formation of these ions is carbon 4 negative is formed very difficultly compared to nitrogen 3 negative, compared to oxygen 2 negative, compared to fluoride ion. Thus, fluoride is formed very easily. Now, the properties of ionic compounds. Physical state. The ionic compounds contain oppositively charged ions which are strongly attracted to each other. Hence, these are hard substances existing as crystalline solids at room temperature. Their melting and boiling points are very high due to strong electrostatic forces of attraction between the ions. Direction of bond. The ionic bond is directionless and the electrostatic force of attraction are present in all directions around an ion. Hence, there is no isolated discrete molecule in the ionic crystal. Entire crystal is considered as the giant molecule. The ionic compounds do not exhibit isomerism due to non-directional nature of ionic bond. Electrical conductivity. In the solid state, the ions cannot move freely and hence they do not conduct electricity. However, in the fused state or in aqueous solutions, the ionic compounds show electrical conductivity due to presence of free moving ions. Solubility. Ionic compounds are polar in nature and hence they are soluble in polar solvents like water. However, these are not soluble in non-polar solvents like benzene, carbon tetrachloride, etc. Reactivity. The reactions between ionic compounds in aqueous solutions occur very fast due to the presence of separated ions. For example, a white precipitate of silver chloride is formed instantly when aqueous solution of sodium chloride and silver nitrate are mixed together. Now let us discuss the energetics of formation of ionic compounds. The major steps likely to be involved in the formation of ionic compounds can be summarized as: first, formation of gaseous atoms. Second, the formation of cations from gaseous electropositive atoms. Third, the formation of anions from gaseous electronegative atoms. Fourth, formation of ionic crystal from gaseous ions. In case of nonmetals, which usually exist in molecular form, an additional step of conversion of gaseous molecules into atoms is required. The energy required for this process is known as bond dissociation energy. The amount of energy required during the initial steps like fusion, vaporization, sublimation, bond dissociation, removal of electrons, etc. is usually more than compensated partly by electron gain enthalpy and mostly by lattice energy. Now, let us discuss what actually lattice energy of a crystal is. The amount of energy liberated when 1 mole of the crystalline substance is formed from the constituent gaseous ions is called lattice energy, represented by the symbol capital U of the crystal, and is calculated using Born-Haber cycle. Born-Haber cycle. The principle involved in Born-Haber cycle is Hess's law of constant heat summation, which states the total energy change in a reaction remains same whether the reaction takes place in one step or in several steps. Let us discuss the Born-Haber cycle for the formation of sodium chloride. In the formation of sodium chloride, we have various processes taking place. The first process that takes place is the sublimation of sodium solid to sodium gas. Sodium gas is then converted to Na positive ion, that is sodium positive. In the process, we have to supply an energy that is equal to the ionization energy of sodium. Similarly, chlorine gas has to be converted to chlorine atom. So for this process we have to supply an energy which is equal to half of the dissociation energy of chlorine molecule. Chlorine gas gets an electron and gets converted to chloride ion in its gaseous state. In the process it undergoes an energy change that is given by the electron gain enthalpy of chlorine atom. Now the sodium positive, that is sodium cation, and chloride negative, that is chloride ion, they form sodium chloride crystal in its solid state. The energy change that takes place in this process is called the lattice energy. Overall, in the whole cycle we have the direct conversion of sodium solid and chlorine gas into sodium chloride crystal. The energy change that takes place in the process is called enthalpy of formation of sodium chloride. The enthalpy of formation delta HF, that is equal to delta H sublimation plus delta H fusion plus 1/2 of delta H dissociation of chlorine plus electron gain enthalpy delta He plus the lattice energy, that is delta Hu. We will have lattice energy U equal to delta Hf minus delta Hs minus delta Hi minus delta Hd divided by 2 minus delta He. So for sodium chloride, when this whole energetics is calculated, it turns out that the lattice energy of sodium chloride crystal is equal to minus 769.97 kilojoules per mole. Born-Land equation. The lattice energy of an ionic crystal is equal to the sum of attractive and repulsive forces in the crystal. It can be calculated by using Born-Land equation as follows. Lattice energy is equal to negative of N0 A Z positive into Z negative divided by R plus N0 B E square divided by R raised to power N. The first part of the equation is the attractive force and the second part of the equation counts for the repulsive force between the two oppositively charged ions. In the equation, the various terms can be defined as A is the Madelung constant which depends on geometry of the crystal. This repulsion coefficient depends on the structure and approximately proportional to the number of nearest neighbors. And 0 is Avogadro's number. Z plus and Z negative are the charges on the positive and negative charged ions. E is the charge of an electron. R is the distance between the oppositively charged ions. N is Born exponent, a constant which is usually taken as 9. Born-Land equation can be written as follows. U is equal to A Z plus Z negative E square N0 divided by R0 into 1 minus 1 divided by N. The solubility of ionic compounds will decrease with an increase in lattice energy. Now let us discuss what polarization is. The negative charge on an isolated anion is evenly distributed around the nucleus, but in presence of a cation, the electron density is distorted towards it. Thus, the negative charge is unevenly distributed over the anion. One end of the anion gets relatively more negative charge than the other end. This condition is referred to as polarization. Due to polarization, the electron density is now spread out in between the anion and cation. This condition is more or less similar to the covalent bonding. The ability of a cation to distort an anion is known as its polarization power, and the tendency of the anion to become polarized by the cation is known as its polarizability. Greater the polarization, the lower is the melting point and heat of sublimation, and the greater is the solubility in non-polar solvents. For example, melting point of potassium chloride KCl is higher than that of silver chloride AgCl, though the crystal radii of Ag positive and potassium positive ions are almost the same. Dipole moment. When two electrical charges of opposite sign and equal magnitude are separated by a distance, a dipole is established. The size of a dipole is measured by its dipole moment mu. Dipole moment is measured in dBi units, which is equal to the distance between the two charges multiplied by the charge. 1 dBi is almost equal to 3.34 into 10 to the power minus 30 coulomb meter. The dipole moment of a molecule can be calculated by the equation mu, which is a vector quantity, is equal to the summation of the product of q, that is charge, into the distance, where mu is the dipole moment vector, qi is the magnitude of the ith charge, and ri is the vector representing the position of ith charge. Equation can be simplified for a separated simple two charge system like diatomic molecule, or when considering a bond dipole within a molecule. For a diatomic molecule, the dipole moment mu diatomic is equal to the product of charge and distance, that is q and r. Consider a simple system of a single electron and proton separated by a fixed distance of almost 100 picometers. When proton and electron get closer together, the dipole moment, that is degree of polarity, decreases. However, as proton and electron get farther apart, the dipole moment increases. In this case, the dipole moment can be calculated as mu is equal to q into r, which is numerically equal to 1.6 into 10 to the power minus 19 coulomb multiplied by 1 into 10 to the power minus 10, that is 100 picometers. This gives a product of 1.6 into 10 to the power minus 29 coulomb meter, which is equal to 1.60 into 10 to the power minus 29 coulomb meter into 3.336 into 10 to the power minus 30 when converting it to dBi units, and the sum comes out to be equal to 4.80 dBi. That's all in this lecture. Thanks, dear friends.